All right, hey AP Physics C. So this is Horner, and this is 2010 number 3. We do have a skier. Skier's going up a hill. It's attached to a rope. Starts at velocity of 0 and then accelerates. So the magnitude of the acceleration of the skier as a function of time, t, can be modeled by a couple of equations. So the first equation is the acceleration is equal to the maximum acceleration times the sine of pi times that time divided by t, where both a max and t are constants. And we'll notice that this equation predominates when our value of t is less than big T but greater than 0. And then if our value of t is equal to or greater than big T, then our acceleration is 0. The hill is inclined at an angle of theta above the horizontal, and friction between the skis and the snow we really don't worry about. And they want us to do everything in terms of the given quantities, and anything that's fundamental is terms of constants. So first thing they want us to do is derive this equation. So the very first equation that we have here is the velocity we know is just the integral of acceleration times dt. But because we're dealing with limits here, we really need to rewrite this. And so I would rewrite it and say v is equal to the integration. That was a terrible integration sign. Let's try that again. The integral of 0 to little t, and that is times a t dt. And that looks a little bit better. So now at this point, we need to go ahead and evaluate the integral. So here we're going to say that v is equal to 0 to t, and our acceleration here is a. This a right here is now what we see here, so it's a max times the sine of pi times t all over t dt. So it's this whole thing. And then if we go ahead and evaluate the integral a little bit more, we remember that we'll use our cyanide strychnine cookie, our double stuffed cookie of death. So it's cyanide strychnine, and we're starting with sine, positive sign. We're integrating, so we're going to move up and not down. So we're going to go from positive sign to negative cosine. So at this point, we're going to do negative a max, and then this will be times t all over, and then we have pi on the bottom, so we're just evaluating this part of the integral. So the t goes on the top, pi goes on the bottom, this t goes away, and then that's times cosine of pi times little t over big T, and we are going from 0 all the way up to little t. So now at this point, I'm going to continue it down here even though it's not part B, so let's scratch this off. If we continue with our integration, we're going to end up with v is equal to negative a max times t over pi, and then we can do cosine of pi times t over big T minus 1, because we're just looking at this t becoming 0, and so now we've got cosine of 0 is 1, and now we can just make it a little bit cleaner by getting rid of the negative. So here we've got a max times t all over pi, and then we're going to do 1 minus the cosine of pi times little t over big T. So all I did was I just took the negative sign, multiplied this whole thing by a negative. When I do that, I end up with this this equation on the bottom. So that was just to get rid of the negative in the front. That makes it a little bit easier. So let's go ahead and take a look at part B. For part B, it says derive an equation or an expression for the work done by the net force on the skier from rest until terminal speed is reached. We know that work is equal to 1/2 of mass times the final velocity squared minus the initial velocity squared. Now what we have to do is substitute everything in for our final velocity. So final velocity would be equal to, and then the t here really is standing for terminal velocity. And that's equal to what we said earlier, which was a max times t all over pi times 1 minus cosine of, now we're going to put in pi. Why do we put in pi? Because now we're looking at it at the t. So in the equation that we had before, it was pi times t. So if you think about it, it was cosine of pi times little t over big T. Little t now becomes big T because we're substituting it in based on our integral. And then these go away. So it's 1 minus the cosine of the angle. And if you do cosine of pi, we're going to end up with 1 minus the cosine of pi, which is 0. And we're going to end up with 2 times a max times big T all over pi. So that's what we're going to end up with. So we've got that 2 comes out front too because the cosine of pi. So 1 minus cosine of pi, and we bump that 2 out to the front. We need to look at the initial velocity, which is VO, because it is 0, and that's equal to a max times capital T, and that is over pi, times, and then we're going to do 1 minus the cosine of 0. And now this is going to be equal to 0. So in the end, we're going to say work is equal to 1/2 of the mass. And then here we need to do the final velocity squared. So our final velocity is this equation. We don't have any original velocity, so we don't worry about it. So this is going to be 2 times the acceleration maximum times the time. And then we divide that over pi, and then this whole thing is squared. At this point, we can go ahead and square this side. When we do that, we're going to go ahead and do our math. We end up with work is equal to 2 times the mass. So here's our mass, times, and then this is going to be a squared max. So our maximum acceleration squared times time squared all over pi squared. So we just squared this. When you square the 2, it makes 4. 4 divided by 2 is going to give us our 2, and that's where it comes from. So a little bit more algebra here than any calculus that you would do. For letter C, we're going to go on down to the next part here. It says determine the magnitude of the force exerted by the rope on the skier, and then it does say at terminal speed. So for this one, we're just going to say the net force. So F net should be equal to the force of the rope minus mg sine of the angle, and that should be equal to ma. So I think the best thing to do here is we really need to go back to that picture that we had before and really look at that picture. So all I'm going to do is I'm just going to move this so that you can see the picture while we still look at this equation so we can figure out where all this came from. Got to move it up a little bit more here. Here we go. Okay, so now you can see kind of the guy there in the skis. We know that he is on an incline, and so we're going to do a free body diagram here. This points straight down, and it would be mg. We know that we have 2 lines, one there and one here. This would be mg, and if we know this angle theta, we also know that this is the same angle. This is mg cosine of the angle, and then this would be mg sine of the angle. And we know that the rope is pulling him in this direction, so that's the force of the rope. If we look at all the forces that we have, we notice that the rope goes first, so that's what's pulling him up the hill. And then there is a force going down the hill, which is mg sine of the angle, and that's why we've subtracted it. And that should be equal to the mass times acceleration going up the hill. So that's where this equation comes from. And I'm going to get rid of our little picture that we have down here on the bottom so that we can go back to the part of the problem that we're working on. And so I'm going to scroll back down here, and it wants to know the magnitude of the force exerted by the rope, and so that's what we're looking for is F rope at terminal speed. At this point, we know, I got to go back on the other side here too. We understand on this one that the force of the rope then should be minus mg sine of the angle. And at this point, if it's at terminal speed, we know our acceleration is 0. So this term crosses off and becomes 0. So now we just say the force of the rope is equal to mg times the sine of the angle. So that makes it pretty easy. The last part here is they want us to talk about impulse. And if you remember, when we talk about impulse, we can look at a force times time graph, or a force time graph, so force versus time, F, T. And if I have any shape here at all, the area of that shape is F times T, which is equal to J, and that's impulse. Now, in calculus, remember, the area of this curve is actually the integral, so we're going to say J, which is impulse. So remember, impulse is J, is equal to the integral of F times dt. So let's go ahead and take a look at this. So J here is equal to, we know that force is equal to mass times the maximum acceleration. And we're doing this from 0 to t. And this is the sine of pi times t over t dt. We go ahead and evaluate the integral here. So J is equal to ma max times t all over pi. So that's what we've done on this side, is we've just switched it. And we're going from sine again back to negative cosine. And we go ahead and put in our variables that we had before. And we know that we're evaluating this integral from 0 to capital T this time. For evaluation of the limits of integration, we just need to say J is equal to m a max times t all over pi. And now if we do this from 0 to t, if you put t in on the top here, we notice the t's cross off, and so you get negative cosine of 0, oops, sorry, negative cosine of pi. I'm getting ahead of myself. And we're going to add that to the cosine of 0. At this point, we can now go through and just say that J should be equal to 2 times the mass times the maximum acceleration times t all over pi. And again, it's because of what we can do with our negative cosine of pi plus the cosine of, and that's not the angle, that's really 0, which is cosine of 0. So cosine of pi, we know would be 2, and so we put the 2 out front, and this is 2 times ma max times t all over pi. And that is your final answer for this problem. I don't think I clarified this very well, so let's just take a look at this one more time. Negative cosine of pi, make sure your calculator is in radians. If it's not in radians, this won't work out, but negative cosine of pi is 1, and the cosine of 0 in radians is also 1, so that's why we get our 2. And then that 2 is what we multiply times this guy right here, and that's why our little equation works out. And that is a better ending.